Okay, in this video we're going to differentiate f of x equals x to the power of 10 using first principles, and that's a power function, of course, x to the power of 10. And this is an ambitious first principles, but keep in mind we're trying to free ourselves from the shackles of first principles for power functions in this video. So it'd be worthwhile, I guess, struggling with first principles for one or two more examples here, and then we'll break free from it. So basically my plan is once we differentiate this using first principles, we're going to immediately generalize that and prove how you can differentiate any power function using first principles. And the good news will be at the conclusion of that, in 10 or 15 minutes time, we'll have a shortcut that can differentiate a power function for us, and we do not have to use first principles. So unless, of course, it's stated in the problem like it is here, which is our only recourse right now for the derivative anyway, is first principles. So we only got this option based on our tools in our toolbox, but also the wording of the question, I guess. So the limit as h goes to 0, I'm setting up my first principles definition, and we have to input x plus h into this power function, and that's going to be a bit of a work to expand that. And then we'll subtract the power function. F of x plus h minus f of x, of course, is our difference quotient, and then all over h. Okay, so we need to expand x plus h to the power of 10. Like I say, that's a bit ambitious, but unfortunately necessary here. So we'll rewrite our limit. So first term is going to be x to the power of 10. That's good. We got one down. 10 more to go. So remember, there's actually 11 terms in a power of 10 expansion. One more than you would think, I guess. Now, of course, we could write out the first 10 rows of Pascal's triangle, but that's honestly a really bad idea because that'll take some time. So remember, to get a row in Pascal's triangle, if it is the 10th row you want, you can actually do it with combinations. Now, we just glossed over what combinations basically were in our course. And I think IB glosses over it even more than that. They just give you this formula and say, hey, these are going to give you your binomial coefficients that you need when you're expanding something like x plus h to the power of 10. So what I'm listing here is not all of them, but of course, if we start at 10, choose 0, all the way up to 10, choose 10. I guess that also explains why there's 11 numbers in this expansion, or 11 terms in this expansion, but this will give us 11 different numbers, of course, that would be in Pascal's triangle, the 10th row. So let's maybe keep in mind, we know the first one is 1, we know the last one is 1, because every Pascal row starts and ends with 1. We know 10 choose 1, that's just going to be 10. And similarly, 10 choose 9 is 10, because remember, there's symmetry here. So if we can get 10 choose 2, we're in business. And if you have your formula booklet handy, you will know how to get 10 choose 2. You can follow along with me here. The formula is the first number on the top, 10, factorial. That goes on the top. And remember, factorial is counts down to 1. And you're multiplying all the digits from 10 down to 1. And then the difference of those two numbers goes on the bottom. So that's 10 minus 2 factorial, and then the second number, 2, goes on the bottom, again with a factorial. So what we do on the top is we can start counting down. I guess we could go all the way to 1, but we'd be wise to stop at 8 and rewrite it with a factorial, because of course there's an 8 factorial on the bottom. And then we got our 2 times 1 there, which is our 2 factorial. So we can divide those 8 factorials, and we're left with 90 over 2, or 45. So that means this number is 45. And I didn't bother writing it down, but 10 choose 8 would also be 45. So that should be enough to finally go back to our expansion here and start using our Pascal numbers. We only need the first couple and the last two, so what I wrote down there should actually suffice. So the second term is going to be the Pascal number, 10 choose 1, which is 10, and then x goes down to 9, and h appears for the first time. And then the third term will be 10 choose 2, which is 45. And then x goes down to 8, and h goes up to 2. Remember, your exponents have to add to the 10, since this is a binomial expansion to the power of 10. And then I'm just going to go ... and say that's going to carry on for a while until we hit another 10. Keep in mind that's the last time we'll see x, so that'll be x to the power of 1 and h to the power of 9, because the very last term in that expansion will be h to the power of 10. Okay, so we got our expansion done, and don't forget in that difference quotient, we better make sure we get minus x to the power of 10 on the top. And we can draw a line here underneath that and put our h that's on the bottom. And let's get rid of all our combination stuff here at this point, because we're going to need the space. So what's the significance of all this? We can subtract those, and the significance is, do you notice that every single term on the top has an h in it, which of course is pretty predictable with first principles, but that means now that I can divide, back to my gold color here, I can divide that h into everything that's on the top, and then we'll do our limit. So as bad as this looks, and as bad as possibly that x plus h to the power of 10 was, we're going to be left with just a couple of terms to write down. And the first one's going to be 10 times x to the power of 9, because when I divide that first term, you get a cleaner x here, x to the power of 9. When I divide 10x to the power of 9, h by h, the h cancels. And then we'll have 45 x to the power of 8 with an h left behind. And I don't know what the next term is, but I know there's going to be an h in it. And same for the next few until we hit 10x. And that's going to be now h to the power of 8. And our very last term is going to be h to the power of 9. So all my powers of h dropped by 1. And now when I do my limit, everything disappears except that very first term, 10 times x to the power of 9. So here's our derivative. And you can possibly take a guess at what that shortcut actually is. Instead of doing what we just did, there's a pattern, and that 10 coefficient, you can probably guess, has something to do with our exponent. And the 9, you can probably maybe take a few guesses as to how to get the 9, but who needs guesses when we can just look at doing a proof of the general proof of first principles to differentiate a power function, any power function with a positive integer exponent, which we will do next. Okay, so here we are. We're going to differentiate f of x equals x to the power of n using first principles, and this will provide proof of the power rule, which will allow you to bypass this whole messy first principles if you're just trying to differentiate a power function, which we'll be doing pretty much the rest of this chapter. So there's a pot of gold at the end of this rainbow, I guess is what I'm suggesting. So let's set up our first principles definition again, and maybe I should write it out in its entirety. I didn't bother. I just, in the last x to the power of 10 example, I just went right in and did it. So remember, it's f of x plus h minus f of x minus f of x, there we go, all over h. And that's our difference quotient. So in this context, our limit would be, if it's a power function x to the n, the limit as h approaches 0, we would have x plus h to the power of n, and then we would have minus x to the power of n. The top part of our difference quotient, and then yes, just h on the bottom. So we have to expand x plus h to the power of n, and that's pretty abstract, especially if we didn't have that first part of this video with that example looking at how to expand x plus h to the power of 10 to kind of fall back on. So we're going to mimic what we did previously to the now using a power of n instead of 10. So remember, to try to find the nth row in Pascal's triangle, you'd be relying on combinations, and they would all start with n. And the first number in this nth row of Pascal's triangle, wherever it is, would be n choose 0. The next one would be n choose 1, and then n choose 2. And then that will go on for some time, of course, a lot of time depending on how big n is. And then we'd get close to n choose n, but let's just put the last two terms again. So these are getting pretty abstract. N choose n minus 1, and the last number in that Pascal row would be n choose n. So those are abstract, but remember, we know Pascal starts and ends with 1. And then the other ones, I guess, we'll worry about later. We'll just kind of write them into our proof here. And you'll notice how there's only really one of these combinations that we have to worry about. Okay, so I'm going to start writing a bunch of combinations with n. And that's because, of course, we're using our binomial coefficient approach instead of trying to find an nth row of Pascal's triangle. But again, both are one and the same, both of those approaches. So let's go back to our first principles and start to expand x plus h to the power of n. So rewrite our limit. And then if we expand x plus h to the power of n, our first term is going to be x to the power of n. Our second term is going to be n choose 1. And then x is going to drop by 1 unit. And h will appear to the power of 1. And then our next binomial coefficient, Pascal's triangle number, will be n choose 2. And then x will drop another unit, its exponent I should say, that'll go down to n minus 2. And then h will go from 1 up to 2. And let's just go dot, dot, dot. We'll go all the way to the very end. We know we'd eventually end up with just an h to the power, in this case, n. I'll make sure my h's look a bit different than my n's. Okay, so there's not the whole expansion, but enough of the expansion of x plus h to the power of n. And then we have to subtract x to the power of n and our difference quotient, and then put a line under that. And don't forget we got that kind of a problematic h on the bottom, which is why we're expanding this. Okay, so now what? We can go x to the power of n minus x to the power of n, goodbye, and everything else in our numerator has an h attached to it. Now keep in mind, we still have to divide everything by an h, so of all of these, I guess, terms up here, every single one of them, our h's are just going to drop by, the power of h is going to drop by 1 unit. So keep that in mind when we divide by h, and that's pretty significant because there's only one term that's going to be left over that doesn't have an h in it. And then when our limit kicks in here, it's going to wipe out everything. That's really good news. So we're going to have now when I divide by h, so it's going to be n choose 1 multiplied by x to the power of n minus 1. And if I divide that h by h, it's gone. So h to the power of 1 goes to h to the power of 0, which is also 1. And then our next term, n choose 2, multiplied by x to the power of n minus 2, and it still has an h to the power of 1 attached to it. And that goes on for a while, possibly a really long time, but I know every single term in that dot, dot, dot has an h attached to it, and our h to the power of n now will drop by 1, and that will be h to the power of n minus 1. So there is all that's left. And our difference quotient, well, the quotient's gone. We got rid of the h, we got rid of the indeterminate form, and we got rid of this proof, I guess, as well, because now as h goes to 0, the only thing we're going to be left with is n choose 1 multiplied by x to the power of n minus 1. And maybe, just to be clear, and prolong our agony here possibly as well, unintentionally, we're going to substitute a 0 in for that h and another 0 in for this h, just so you can see what I'm talking about, to say, oh yeah, everything that has an h in it now is going to have a 0 in place of that h, and that's all a product in every one of those terms, so every single term is going to disappear. How many? There could be 10 of them, there could be 20 of them, but they're all going to disappear as h goes to 0. So there's our formula for differentiating a power function. So one last thing, let's get rid of that combination. So to get rid of that, we'll have to rely on our combination formula, which is n choose 1 in this case. Will be n factorial. The first number goes to the top. Difference goes on the bottom. Of course, everything has a factorial attached to it now. And then the second number goes on the bottom, which is just 1 factorial. So we can ignore that right away. 1 factorial is just 1, so dividing by 1 is not going to change anything. So we just have to sort out our n factorial stuff here. So remember, when that was 10, we just count down until we match a number that's on the bottom. So we know we should be able to match a number that's on the bottom, and we don't have to go too far. So n multiplied by 1 less than n, we already hit the number that's on the bottom with the factorial that matches. So this is gone as well. And remember, I ignored the 1 factorial because it's equal to 1. So n choose 1 is equal to n. And we can also now get rid of our n choose 1 in our formula. And we can say that our derivative is n multiplied by x to the power of n minus 1. So let's make sure we know how to utilize this. So our original function, I guess I can squeeze in my derivative here. I'll slide this over a bit. This is the derivative, f prime of x. So remember what our original function was. It was f of x equals x to the power of n. So what is our derivative telling us to do? It's telling us to take our power, n, down to the front. If we want to differentiate it, that becomes our new coefficient. It's also telling us our old power decreases by 1 for our derivative. So anytime you differentiate a polynomial, it should drop a degree, which you've probably have recognized in the last couple of examples as well. So let's try to illustrate that maybe a little better with one concrete example. If we got anything left here, it might be it's a lot to cover in one video, but we got an important shortcut now that we can utilize anytime we're differentiating power functions. So let's do one example. We will just say differentiate f of x, a brand new f of x, x to the power of, how about 20? That'd be enough work if it was first principles. And I'm going to put a period. I have no intentions of saying first principles, so that's significant as well in the kind of the rules here. If I don't say first principles, which I probably hardly ever will again, quite honestly, only once in a while to sharpen up your basic first principle chops, not a tedious situation like this. So if I don't say first principles, utilize your shortcuts. So our derivative here is going to be, what's my power? 20. Okay, that becomes my coefficient, and my power drops by 1 unit. And just like that, you're finished. And you might be bewildered right now saying, what? That's it? That's all I have to do? Yes, that's all you have to do to take the derivative of a power function. It was worth the hassle, possibly. Okay, so that's it. In future videos, we're going to be utilizing this shortcut, which incidentally, when we're using shortcuts, you can see in the title of this video, we call these, well, differentiation rules, but maybe I like to call them rules of differentiation. When you're dealing with rules of differentiation, dealing with rules, but most importantly, you're also dealing a lot of the time with shortcuts that allow you to bypass the messy, time-consuming first principles process. So we'll utilize this for the rest of Chapter 5, your new friend called the power rule.